fibrations and four-manifolds, and in particular the way that those things help us understand, those perspectives help us understand problems about surface bundles, symplectic manifolds, and is also really responsible for building a lot of the topology community in that area. And so it's really a great pleasure to have him teach us about Lefschetz fibrations.
So yesterday, we reviewed definitions and basic properties of Lefschetz fibrations and their monodromies. So today, I'd like to talk about construction and classification of Lefschetz fibrations. So since monodromy representation is a homomorphism, it is determined by the images of the generators of the domain. So domain is the fundamental group of a punctured surface. And if the surface is D2 or S2 and the set of generator is nice in some sense, then they are right-handed, finitely many right-handed dent-twist. Okay? So such a collection of right-handed dent-twists is called a monodromy factorization of a given Lefschetz fibration. So let me start with the definition of a full-bit system. So F from X to D2 be a Lefschetz fibration of genus T. So please read this symbol, Lefschetz fibration of genus T. Okay? And C the set of critical values. And the critical values are Q1 to Qn. And Q0 is a regular value of F. And take gamma I from the interval to D2. This is a path from Q0 to Qi. So where I is 1, 2, n. Okay? So definition. So gamma 1 to gamma n is called a Hurwitz system for the triple D2, C, and Q0 if it satisfies the following three conditions. First, gamma I is simple. So that is, it has no self-intersection. Okay? Second, the intersection of gamma y and gamma j is a single point, Q0. If I is not equal to j. Third, these paths are counterclockwise in this order. So this is the definition of Hurwitz system, but I will draw an explicit Hurwitz system to explain the third condition. Okay? So this is a base point Q0, and there are finitely many critical values, Q1, Q2, Q3 here, and Q5, Q4. So there are 5 critical values. And the gamma 1 to gamma 5 are something like this. Okay, so this is gamma 1, gamma 2, gamma 3, gamma 4, and gamma 5. Okay, so here is D2. And if you go around Q0 in counterclockwise direction, then you encounter gamma 1, gamma 2, gamma 3, gamma 4, gamma 5 in this order. So this is the third condition, okay? Next, AI, a map from the interval to D2. This is a loop, so called the meridian loop. Of some I. So I'd like to state, give the definition of AI by using the figure. So this path is gamma I. So gamma I is a path from Q0 to Qi. This is gamma I. Then you can construct a loop by using this gamma I. So starting at Q0, and you follow the path gamma I until you reach a point near to Qi. So here Qi. And then you go around the point Qi in counterclockwise direction, and then you go back to Q0 along the inverse of gamma I. So this loop is called AI. Okay. Then the fundamental group of D2 minus C based at Q0 is the free group generated by n elements, alpha 1 to alpha n. Here, alpha I is the homotopy class of AI. Okay? And rho f of alpha I is equal to the right-handed dentist along some simple closed curve as we observed yesterday. So this is the right-handed Dehn twist. Along CI. So CI is a simple closed curve on sigma g. And I'd like to draw a figure. So here, so this surface is sigma g, and this curve, this simple closed curve is CI. And take a path like this, then the right-handed Dehn twist along CI maps this orange curve to another one. So like this. Okay. And the ordered set of right-handed Dehn twist TC1 to TCN is called a monodromy factorization of F with respect to gamma 1 to gamma n, and also impact phi. So this is the identification of the model surface sigma g with regular fiber over Q naught. Okay. So this is a definition of monodromy factorization. So yesterday, we obtained a monodromy representation from Lefschetz fibration over D2. And conversely, if you have an n tuple of right-handed Dehn twist, then you can reconstruct Lefschetz fibration over D2. So this is the construction theorem. So C1 to Cn, let C1 to Cn be simple closed curve on sigma g. Then there exists a Lefschetz fibration over D2. So this is a Lefschetz fibration of sigma genus G, and a Hurwitz system gamma 1 to gamma n. For a triple D2C Q naught, such that the monodromy factorization of F with respect to gamma 1 to gamma n is equal to the ordered correction TC1 to TCn. Okay. Yes. Yes, thanks. So we should put essential. Okay. So I'd like to give a proof of this theorem only for n equal 1. So proof. For n equal to 1. So we can assume that the set of critical values is zero. And a Hurwitz system, so Hurwitz system, the Hurwitz system consists of a single path, gamma 1, and it is 1 minus t, so we can assume this. So I'd like to draw a figure. So gamma 1 is from this point, this point is Q0, and this point is Q1, and gamma 1 is this path. And let Q, K, A, and F are as before. And eta are mapped from A to Q hat. So Q hat is defined as sigma g minus some open neighborhood of C1. And eta is orientation preserving diffeomorphism between these two. So this is an identification of A with this with the color neighborhood of this surface. Okay, so I draw a figure. So A is a disjoint union of A1 and A2. And both of A1 and A2 are C minus open disks. And eta is a diffeomorphism between this object with a color neighborhood of the boundary of sigma hat. So sigma hat is sigma g minus open neighborhood of some simple closed curve. So sigma hat is something like this. And eta is a diffeomorphism between A and color neighborhood of the boundary of sigma hat. Okay? So I'd like to fix an identification of A and color neighborhood of the boundary of sigma hat. Then we can define a four-manifold X as the pre-image of D2, this joint union is D2 times Q hat divided by some equivalence relation. Here, phi is a diffeomorphism defined as X maps to identity times eta circle F inverse of X. So this is the four-manifold X. And this part is a singular part. So this part includes a critical point. And this part doesn't include any critical point. Okay? So, and let F from X to D2 be a map defined as follows. So X maps to the first projection of X if X belongs to D2 times sigma hat and Q of X if X belongs to the pre-image of D2. Then F is an LFG. So Lefschetz fibration genus G over D2 with vanishing cycle C1. So this is the proof. So, and I'd like to give you an exercise, or two exercises. So please check that F is an LFG with monodromy TC1. Second, please give a proof of the theorem for Q greater than 1. Okay. For the second exercise, you have already know that you can construct a neighborhood of each singular fibers by using this proof. So only you have to do is to construct a surface bundle part. So it is essentially it is constructing some appropriate mapping tori. Okay? So it is. I think it is not so difficult exercise. Okay. So we then describe a similar theorem for Lefschetz fibrations over S2, so not D2. Okay. So next, we'd like to consider Lefschetz fibration F over S2. And we take C rho F gamma I, AI, and alpha I, TCI as before, so as above. Then the pi 1 of S2 minus C based at Q naught has a presentation as follows. So generators are alpha 1 to alpha n, but we have only one relation. Alpha 1 times alpha n is equal to the identity. Okay. So since the composition of alpha 1 to alpha n is homotopic to the constant map, so we have this relation. And then considering homomorphic image of this relation, we have the relation TC1 to TCn is equal to 1 in the mapping class group of genus G. Okay. Then existence theorem for Lefschetz fibrations over S2 is as follows. So let C1 to Cn be essential simple closed curves on sigma G. And we assume that this relation then there exists a Lefschetz fibration over S2, and so and Hurwitz system gamma 1 to gamma n for S2 C Q naught such that the factorization of F with respect to gamma 1 to gamma n is the ordered correction of right-handed then twist, TC1 to TCN. So this is the theorem for Lefschetz fibration over S2. Okay. And I'd like to give you exercise. So please prove this theorem. So prove. So this is also not so difficult because you already have Lefschetz fibration over D2. So you only have to consider how to close, how to make a closed manifold by using a trivial bundle over D2. Okay. So next, I'd like to briefly review the classification theorem of Lefschetz fibration over, in particular, S2. So let Fi be Lefschetz fibration over sigma. So sigma is a compact surface. So this is a Lefschetz fibration. That I is 0 or 1. So we consider two Lefschetz fibrations. And definition. So F0 is called isomorphic to F1 if there exists a diffeomorphism theta from x0 to x1 and small theta from sigma to sigma such that F1 circle theta is small theta circle F0. I have not. So this means that there is a fiber preserving diffeomorphism between x0 and x1. Okay? Next, so let Ci be a subset of the interior of sigma. So this is a finite subset. And take a point Q naught I in this surface. Here also I is 0 or 1. And consider a homomorphism from pi 1 of sigma minus Ci based at Q naught I to Mg. This is a homomorphism. So this homomorphism is, in some sense, an abstract homomorphism, not necessarily coming from monodromy representation, just a homomorphism. Definition. So rho naught is said to be equivalent to rho 1 if there exists diffeomorphism between the triples sigma C naught Q naught 0 to sigma C1 Q naught 1 and P in MG such that the one circle theta star of alpha is equal to P inverse times rho naught of alpha phi for all alpha in I1. Okay. So this is a definition of equivalence between two homomorphisms, two such homomorphisms. Okay. Then I can state the main theorem. So this is, I think this is due to Moishism. Kass and Yukio Matsumoto. So assume that rho I is a monodromy representation of F phi. And also, one of the following is satisfied, that G is greater than or equal to 2, or the boundary of sigma is not empty, or the set of critical values of F naught is not empty. Then F naught is isomorphic to F1 if and only if rho naught is equivalent to the 1. So I don't give any proof of this theorem. So the proof is a little long, so I don't give any proof. Next, I'd like to explain how monodromy factorization changes if you change a full bit system. Okay. So let gamma 1 to gamma n be a full bit system. For sigma, sorry, d2 is 2, c q naught, then definition, the operation and its inverse. Is called an elementary transformation on gamma 1 to gamma n. And the operation is as follows. So take two paths. So these two paths are gamma 1 and gamma I and gamma I plus 1. So these points are qi and qi plus 1. Okay. So this is the initial position. Then I'd like to deform these two passes like this. So q naught and qi plus 1. These 3 points are the same, but this path is new gamma I plus 1. So gamma I plus 1 tilde. And this path is new gamma I, so gamma I tilde. Okay, so we change this Hurwitz system into this Hurwitz system. Okay, this is an elementary transformation. Okay, and there is a theorem. So this is not difficult, but I do not give a proof of this one. So let gamma 1 to gamma n and gamma 1 prime to gamma n prime be two Hurwitz systems. For the triple. Then qi primes are obtained from gamma I primes are obtained from gamma i's by finitely many elementary transformations. and cyclic permutations. Next, I'd like to introduce three kinds of moves for n tuple of right-handed dent twist. So, definition. So, Hurwitz moves. For n tuple TC1 to TCN. So first kind of moves are like this. So if you have initially you have such finite collection of right-handed dent twist. Then you can change this into TCI, TCI plus 1, TCI inverse, comma, TCI. Second move. This move is called simultaneous conjugations. So this collection is changed into the conjugates of the original collection. By the same phi. The third move, this is the cyclic permutation of these right-handed dent twist. So these three moves are called Hurwitz moves for the collection of dent twists. And finally, we have the following conclusion. So that this is an exercise for you. So assume that G is greater than or equal to 2, or the set of critical points is not empty. Then there is one-to-one correspondence between the set of Lefschetz fibrations of the set of isomorphism classes of Lefschetz fibrations over S2 with n singular fibers. So this set divided by isomorphism. And there is one-to-one correspondence. And the set of n tuples, so ordered n tuples of right-handed dent twist, which satisfies the relation TC1 to TCN is equal to 1 divided by equivalent. No. Hurwitz move. Okay. So please use two theorems above. So this one and this one to prove this statement. Okay. So I think it is not difficult. So it is a little early, but I will stop here. So thank you very much.